This presentation is on Rabin Cryptosystem. This technique was published in January 1979 by Michael O. Rabin. Rabin Cryptosystem has an advantage that the problem on which it relies has been proved to be as hard as integer factorization. Rabin Cryptosystem, it is based on quadratic congruence, whereas its variation RSA algorithm, it is based on exponential congruence. This figure shows the complete procedure of Rabin cryptography. Initially, we have key generation where n is the public key, it is equal to p into q. P and q are private keys and they are prime numbers. And encryption is p square mod n, and decryption is square root of c mod n. Here Alice is trying to send a message to Bob and Eve is trying to steal the message. This cryptography uses both public and private key. In the key generation phase, first we select two large distinct prime numbers which are either congruent to 3 mod 4 or 1 mod 4. It is preferred to use 4k plus 3 form to make decryption for the concerned person easier. N is equal to P multiplied by Q is the public key, and the prime numbers P and Q are private keys. Only public key is needed for encryption. Suppose M is the plain text. It is chosen from Zn star to make decryption easier. Ciphertext C, it is the quadratic remainder of the square of the plain text modulo the public key N. Decryption is based on the solution of quadratic congruence. Basically, the plain text is the square root of ciphertext modulo public key. Now, because the received ciphertext is the square of the plain text, it is guaranteed that C has the roots or the quadratic residues in Zn star. There is a disadvantage here that we get 4 square roots, out of which only one will be our plain text. Chinese remainder algorithm is used to find the 4 square roots. First, we compute A and B. A into P plus B into Q is equal to 1 by Euclidean algorithm. And next, we compute R. R is equal to C raised to the power P plus 1 divided by 4 modulo P. C is the ciphertext. P is one of the private keys. S is equal to C raised to power Q plus 1 divided by 4 modulo Q. C is the ciphertext and Q is one of the private keys. X is equal to A into P into S plus B into Q into R modulo N. A and B we have computed above, and N is the public key. And Y is equal to A into P into S minus B into Q into R modulo N. We get 4 square roots as m1 is equal to x, m2 is equal to minus x, m3 is equal to y, m4 is equal to minus y. If the plain text is a string, then we can find the correct plain text by looking at its meaning. But if it is random or some numeric string, then selecting one out of the 4 possible plain text is difficult. Thus, the solution to this problem is that we introduce redundancy in our plain text. One method is to pad the message by replicating its bits. Another method is appending preset bits to the message, and later at decryption, correct preset bits are checked. Let's take an example. Let the decimal plain text is equal to 5. For knowing the correct message later, we replicate our bits. It then becomes 45 in decimal. P and Q we have selected as 11 and 7. They are prime numbers, and the public key then becomes 77, which is 11 into 7, and the private keys are 11 and 7. For encryption, we simply do square of plain text modulo public key, that is 45 square modulus 77, which is 23. Now for the decryption process, we start by A into P plus B into Q equal to 1 by Euclidean algorithm. We compute A and B. We get A is equal to 2 and B is equal to minus 3. Now we need to compute R, S, X and Y. R is equal to ciphertext to the power P plus 1 divided by 4 modulo P equal to 1. S is equal to ciphertext to the power Q plus 1 divided by 4 modulo Q, it is 4. X is equal to A into P into S plus B into Q into R modulo N, it is 67. A into P into S minus B into Q into R modulo N equal to Y, it is 32. Hence, the roots we get are M1 is equal to X, that is 67. M2 is equal to minus X, that is minus 67 plus 77 equal to 10. M3 is equal to Y equal to 32. M4 is equal to minus Y, that is minus 32 plus 77 equal to 4. We have to avoid negatives, so we add 77. Out of the 4, to select one, we convert all into binary and find that 45's binary has replicating bits. 101 is being repeated. Hence, the correct plain text is 45. We remove the replicating bits and get 5. Let's discuss about the security of Rabin crypto system. It works well for passive attacks because n is the public key, but to calculate its factorization, because it is n is equal to p into q, and to calculate p into q, finding p and q, it's hard. But this method is insecure against chosen ciphertext attacks, because if he gets the ciphertext and form ciphertext plaintext pairs, then P and Q will be easily calculated. Private keys are calculated, then the plaintext can be easily found.